Welcome back to Students Teach Orgo. This will be the first video in a series regarding chemical reactions with enols and enolates. In this first video, we'll just go over the basics, and I'll start by talking about the formation mechanism right after a brief introduction here. So far in Organic Chemistry 2, we've seen a lot of reactions that involve compounds with carbonyls, a lot of carbonyl chemistry. And so far, the typical format of these reactions is that we have a nucleophile attack the carbonyl carbon. And remember that carbonyl carbon is an electrophile because it's got this partial positive charge. Oxygen is a very electronegative atom, so it's kind of hogging the electrons to itself, which makes this carbon right here electrophilic. A nucleophile attacks it, and we get a tetrahedral intermediate and go from there. If you've been following the Orgo 2 concept so far, I'm sure you've seen this before. However, this video will introduce the idea that carbonyls can sometimes live this double life where instead of being an electrophile, they have more nucleophilic characteristics. And this happens when the carbonyl form isomerizes into the enol or enolate form. Now, this is a special type of isomerization called a tautomerization. And just to explain that jargon, tautomerization is when just a proton changes places. So you can see in the carbonyl form, we've got this hydrogen atom right here. But in the enol form, that hydrogen atom moves up to the oxygen, and we get that double bond. And another important thing to point out here is that the enol form and the carbonyl form interconvert. And so there's this equilibrium. And so whenever I show you these two forms, especially in aqueous solution, I'll have that equilibrium there, arrows there to show that it goes back and forth. I figured I should have this slide here just to really clearly spell out the vocabulary, the words I'll be using a lot in this video. An enol and an enolate are both very similar chemically. You can see the only difference is over here this oxygen is bound to the hydrogen atom, and over here it's got a negative charge. And so you'd most likely find an enolate in base, and most likely find an enol in some sort of acid. And so without further ado, we should start talking about the mechanism for enol formation. Alright, so when in acid, the first step is that the oxygen of the carbonyl is going to attack a proton on hydronium, and that will leave us with water and that protonated carbonyl compound. Now, once we get to this part, water is going to act as a base, and it's going to extract a proton from the alpha position to this carbonyl. The electrons that were holding together that carbon-hydrogen bond are going to go to make that double bond right here. And these electrons that were part of the carbonyl will jump up there to neutralize oxygen. And that is how we'd make an enol. Pretty straightforward, not a super long mechanism. What I want to point out here is that it's also reversible. So if we start with the enol, we could have an electron pair on oxygen drop down. This carbon right here is going to attack that hydrogen, and then water would extract another proton again to go back to the carbonyl form. And so just to spell it out very clearly, this carbon right here is the nucleophilic carbon on an enol. Sometimes when we draw this arrow right there, students get confused and say, oh, well, I know this double bond is attacking a proton, but how do I know if the proton goes to that carbon or to that carbon? Well, when we drop these electrons down, this carbon right here will have its octet filled. It'll be connected to 4 different things. So that proton has to go to this carbon right here. And so I just wanted to draw these resonance structures here to show you that this is a valid resonance structure of the enol form, and that there's a partial negative charge on that carbon, which contributes to it being nucleophilic. Alright, and now for the enolate formation mechanism in aqueous base. So the first step is that hydroxide is going to extract that proton from the alpha position of this ketone here. We will push the double bond, the electrons that make the pi bond, up onto the oxygen to get a negative charge, and it's that simple. Just that those 3 arrows right there are all you need to know to make an enolate in base. And down there is the reverse reaction, just as simple. We can take the negative charge, the electrons up on this oxygen, push them down. This nucleophilic carbon will grab a hydrogen, and we've taken apart our enolate. And so for the first practice question here, I would highly recommend drawing out those curved arrows yourself and practicing the interconversion between the keto, I guess this is a ketone, that's an aldehyde, so the conversion between the carbonyl form to the enol and the transition from the carbonyl form to the enolate. Pause the video, do that. There's the answers. Pretty self-explanatory based on the last few slides. Alright, the largest part of this video is going to be talking about factors that determine the equilibrium between the keto or the carbonyl and the enol form, so the interconversion between those two. So this slide features the chemical structure of acetone, which is a really common molecule you'll find in daily life. It's commonly used as nail polish remover. And I've specifically drawn in the bond between this carbon and this hydrogen because when you're going back and forth and tautomerizing between the keto form and the enol form, this bond would be one that breaks. And in this case, the KEQ value for the equilibrium between acetone and 2-hydroxypropene is 10 to the minus sixth. And so if that number doesn't mean much, I've got just a little equation here for KEQ, which is products over reactants. So in this case, we're considering this to be the product, and we're considering this over here to be the reactant. And a really small KEQ value means that we have a lot more reactant than we do products. So a whole bunch of reactant, not a lot of product. And what that means is if you had acetone in a container, most of the molecules would be in the keto form, and just 1 in a million, literally a million, 10 to the minus sixth would be 1 in 1 million, would be in this enol form. And so I think this might be not super helpful, but I thought it was fun. So imagine that you've got this big beaker full of acetone. I know I don't have a million drawn there, but you can see just the one down there is in the enol form. So there are 4 main factors that can shift that equilibria. Not every single ketone is going to have that KEQ of 10 to the minus 6. And so you can see the 4 factors that are listed there: substitution, conjugation / resonance, hydrogen bonding, and aromaticity. And on the right here, I have a comparison of 2 molecules that tries to highlight how that particular factor could change the balance. And so I'm going to go through all 4 of these one at a time here, starting with substitution. So the general rule here is that the more substituted the double bond is in the enol form, the more that molecule will favor the enol form. So this aldehyde right here is called acetaldehyde, and when that interconverts into its enol form, you can see that the double bond is not very substituted because none of the substituents, nothing attached to the double bond, is a carbon. They're all these hydrogens and that OH. And so that makes this molecule much more unstable than these 2 molecules beneath it, that this one has the 1 carbon and this one's got 2 carbons. And so these molecules that have more carbons are going to be more stable in their enol form, which will shift the equilibrium toward that enol form. And so I've got the KEQ values for this top molecule and this bottom molecule down here, and you can see that 10 to the minus fifth, that's a smaller KEQ, which means this favors the reactant more, and 10 to the minus fourth is a slightly bigger KEQ, and so that will favor the enol form more than this one, right? So to test this concept, we've got a practice question here, and this question asks you to order the protons, right? Proton number 1, 2, or 3, in respect to increasing acidity. And so I know that for someone watching this video, it might be slightly confusing, like, hey, we've been talking about, the equilibrium between the keto form and the enol form. What does acidity have to do with anything here? Think about how proton acidity, the willingness of a molecule to give up a proton, could impact that equilibrium. So I'll give you a second. Try to do this problem on your own. Rank them: most acidic, least acidic. Alright, I'm going to go ahead and show the answer now. So it turns out that 2 is the most acidic and 1 is the least acidic. And if we wanted to think about this kind of in a lens from Orgo 1, we can imagine that when a base or a nucleophile takes a proton away from a molecule, that parent molecule will be left with a negative charge. And so if we look at the 4 different anions that would be created from removing this proton, or this proton, and then judging their stability, we should be able to determine which is the most acidic. And the ARIO acronym, that's something you learn in Orgo 1. A stands for atom, R for resonance, I for induction, and O for orbital. All 3 of these hydrogens are attached to the same atom, so the A doesn't matter, but R stands for resonance, and that negative charge that'll be left when you take that proton, the resonance structures will be different. So this is the R in ARIO, I guess. So in 2, you can see that this negative charge on this carbon, we can move that negative charge to the oxygen and create this enolate. And so this is how this question relates to enolates equilibria, in that this enolate is going to be the most abundant enolate. Well, it'll be more abundant than this second enolate down here, and it's going to favor this enolate more than it would favor this enolate. I guess that's kind of what I just said before. But the reason why is because this double bond is more substituted. This has 3 carbon substituents, 1, 2, 3, where this enolate down here only has 2 carbon substituents, 1, 2. And so that's the idea. They'll ask you questions about this and ask for which is the more acidic proton to test your knowledge of the equilibria between the carbonyl and enol or enolate form. Alright, the next factor that can determine the equilibria between the carbonyl and enol or enolate form is conjugation or resonance. So we've got these 2 molecules right here. This is benzene, this is cyclohexane, and so you can see the difference between these 2 enol forms is that this enol form right here is more conjugated. There's a larger pi system. This double bond is in communication with all the double bonds in the benzene, where up here this double bond is just by itself. And so if you look at the KEQ values, you can see that 10 to the negative 7th is larger than 10 to the negative 8th. So this enol form will be more favored than this enol form because of conjugation. Now I also want to point out here, this molecule right here could have 2 different enol forms, right? We could have plucked this hydrogen to make an enol that would have had the double bond there instead of here, or the one shown. Now I want this can be very important. This ketone, right? This carbon is what we'd consider to be non-enolizable. And all that means is that you can't make an enol on this side because there is no alpha proton. So the only enol you could possibly make is on this side. And that will come up more when we talk about crossed aldol reactions, but an important point to make right now. And so here is a practice question regarding conjugation and resonance and how that would impact the equilibrium. So I'm asking you to pick out which molecule would have the highest KEQ, or in other words, which molecule is going to most likely be in the enol form, which one is going to be most comfortable in the enol form. So pause the video. I made this question myself. It's pretty good. Alright, I'm going to go forward now. The answer would be D, and the explanation would be that this is the only molecule where the negative charge made from creating an enolate would be able to resonate more than just between the carbon and the oxygen. So you can imagine that there's a hydrogen right here, and if we had some sort of base take that hydrogen, and that would leave a negative charge on that carbon. This negative charge could be on that carbon, it could be on that oxygen, or it could be on the oxygen on the other side. So that negative charge is delocalized between 3 atoms, and that resonance is going to stabilize that enolate form a lot and make it much more likely that that molecule will be found in the enolate form. So you can see a KEQ of about 0.5, that's much higher than any other KEQ value we've seen so far. However, with A, B, C, and E, that that enolate, the negative charge would only be delocalized between two atoms, right? It could be between the oxygen or those two. Here it could be between this oxygen or those two. This molecule also has two ketones, but notice that because these two ketones are far enough away, you don't get the resonance that you'd get in D. Here's a second practice question about this concept. Again, I'm asking you I'm asking you about the equilibrium constant, but this time try to rank them in terms of increasing KEQ. So I'll give you a second to do that. Pause the video. Alright, I'm going to go ahead and show the answer. And we can see that B is going to have the highest KEQ, followed by C, and then A is going to have the smallest KEQ. And the explanation for that is that A, C, and B are three different functional groups. We have an ester, we have a ketone, and we have an aldehyde. And so the enolate forms of the aldehyde, the ketone, and the ester are all going to have slightly different stabilities based on just their structure as a functional group. Now, the reason the ester has the smallest KEQ is because of a phenomenon known as competing resonance. So you can see I've drawn the enolate of the ester here, where we've plucked a hydrogen from here, and we've got a negative charge on this carbon. Now, there's two different sets of arrows. There's the red arrows and the blue arrows, but you can see we could either take the negative charge from this carbon and put it on the oxygen, and that would give us a pretty traditional looking enolate right there. But we could also take the lone pair on this oxygen and push it up and have this positive charge on this oxygen, negative charge on this oxygen. Basically, the idea is that because there's two different atoms that could take their electron pair and push it up onto that oxygen, they're going to compete against each other. And so the delocalization on any one side is going to be half of what it normally would be. And so because this enolate can't distribute that negative charge as well as it normally could, it's going to be very unstable in its enolate form, and so most of it is going to stay in this ester form. Now, the difference between ketones and aldehydes is a little bit different. Ketones have to have these two alkyl groups, right? And the aldehyde only has the one alkyl group, and then the other side has to be a hydrogen. That's what just makes it an aldehyde. And so because of the electron density surrounding that carbonyl carbon, the ketone is going to tend to be more stable, and it's going to favor the keto form more. But with the aldehyde, because this carbonyl carbon is less stable, it's more apt to form the tautomer. The next factor is hydrogen bonding. I want you guys to take a look at these two molecules right here. They're both diketones. They're molecules that contain two ketones in them. But the difference is that this molecule, the two ketones, both share an alpha carbon. Right? This carbon would be alpha to both this ketone on the right and this ketone on the left. Where down here, this would be an alpha carbon to this ketone, and this would be an alpha carbon to this ketone, but there's one in the middle, like another carbon that separates the two of them. And this is going to make a big difference as far as where the equilibria shifts between these two molecules. You can imagine if we were in acid and this carbonyl was protonated and we had some sort of base, water or something, pluck this proton and turn this into an enol, we would get an enol that looks something just like this. And because of that spacing between the two ketones, we would form this intramolecular hydrogen bond, which would greatly stabilize that enol form. And so the KEQ for this molecule would be much higher than it would be for this molecule, where in the enol form, it's just too far away for that hydrogen to interact with this oxygen. And so this is a trickier concept for them to test or quiz you on, but you'll still find it once in a while. So this practice question, this is going to be applying that principle of hydrogen bonding to shifting the equilibria. Which molecule would be more likely to be found in the enol form? Now this is tricky because on this last slide here, this molecule had a carbon in between the two alpha carbons, and this molecule had the alpha carbon that was shared between the two ketones. Both of these molecules have that carbon, right, that's in between two ketones. That both of these hydrogens would be relatively acidic compared to most carbon-hydrogen bonds. But thinking about that hydrogen bonding, I want you to try to think about which one would be more likely to be found in the enol form, or have a higher KEQ. Alright, pause the video. I'm going to go forward here. The answer would be this one. And the reason is that the ring here, the fact that these two ketones are locked in a ring, would prevent that hydrogen bond from forming. So you can see that with this molecule, we can rotate the single bonds, and if we turned it into the enol form, we can draw it like this. Well, sorry, this is how it's drawn over here, but we can rotate the single bonds to make it look like this. And when we rotate those single bonds, we can see how that intramolecular hydrogen bond could form, which would stabilize it. This one over here can't do that, right? Because when we would go to make the enol form, it would look something like this, OH, and over here that double bonded O. And you know what, even if I decided to draw that H on the other side here, this carbonyl and that hydrogen are just too far away for there to be that hydrogen bond. And so that would be a good explanation as to why this KEQ is 7. That means it's more likely to exist in the enol form than in the keto form, where this one's just around 0.5 again. And the last factor is aromaticity. If you want to review your rules on aromaticity, we've got a video on our YouTube page. But the idea here is pretty simple. If creating an enol would give the molecule aromaticity, that will greatly shift the equilibria to favor the enol form. So you can see this is 3 ketones here, but if all 3 of them go into their enol form, we would create this aromatic benzene ring. And so, you know, it's much easier for these hydrogens to get pulled because you would create that aromatic ring than just a normal cyclohexane ring. Those carbon-hydrogen bonds aren't very acidic, but these carbon-hydrogen bonds would be much more acidic. And so, not much more I need to say about that. Let's just jump right into a practice question. For each case, I just want you to circle which product you think would be favored at equilibrium. So the aromaticity is a really strong factor. If you have the ability to make an aromatic compound, that's probably what's going to be favored at equilibrium. Alright, try that for yourself. And here are the answers. You can see that creating an enol here, moving those electrons like that to make double bond would give you an aromatic ring, so this one would be favored. Down here, we would not be forming an aromatic ring when we go to the enol side, and so this KEQ is basically the same as acetone, right? It's really, really small. And then down here, I was testing your knowledge on aromaticity rules. This compound right here would be anti-aromatic, right? Because if you're thinking about Huckel's 4n+2 rule, there's only 4 electrons in this ring, and so this side is definitely going to be favored. You would not want to make the enol form at all here because you'd be making an anti-aromatic ring. And the last part of this video is just going to be an introduction to synthesis with enolates. We're going to cover this a lot more in depth in the Robinson annulation and Claisen condensation videos, and the aldol video. But this will be a start. So this is an SN2 reaction where I told you before that this carbon in an enol or enolate, this is an enolate, is nucleophilic. And so this nucleophilic carbon can do an SN2 reaction with a alkyl halide, and we can make a carbon-carbon bond. And so making carbon-carbon bonds are very important in organic chemistry synthesis, so we'd want to find a way to control this. Now the problem is, if we did this reaction in water, we would need to make a whole bunch of enolate in order to do this reaction. But we just spent a lot of time talking about how there is an equilibrium between the carbonyl form and the enol or enolate form, and we also wouldn't be able to control for a ketone like this, which side the enolate's on, whether or not the double bond's on this side or whether or not the double bond's on that side. So we want to avoid water when we're doing this kind of synthesis with enolates because it would be really messy, we'd get a whole bunch of products, and there wouldn't be a super great yield because not a lot of our carbonyl compound would be in the form that we need it to be in. So there are 2 main synthetic pathways that we can follow that will utilize enolates in our synthetic process. The first is the LDA path. LDA stands for lithium isopropylamide. You can see the lithium right here, the two isopropyl groups, and our functional group here would be an amine. This is a very, very basic compound. In organic chemistry so far, you usually don't see a negative charge on a nitrogen. But you can imagine that this salt, this would be a salt, and having that negative charge on the nitrogen makes that a very, very basic compound. And these isopropyl groups will give it some steric hindrance, which will be important in a moment. And the other method would be to use chlorotrimethylsilane and pyridine, followed by methyl lithium. And I'm going to introduce these concepts of the less substituted kinetic enolate and the more substituted thermodynamic enolate, because by choosing which path we use, we can control which side of a carbonyl, in some cases, we add our carbons onto. So I'm going to use this ketone right here as an example for both pathways. And what you'll notice is that the ketone has different substitution on different sides. So this alpha carbon is attached to no other carbons except for the carbonyl carbon, and this carbon, this alpha carbon, is attached to these two carbons over here. Now, there's two hydrogens, right? So a base, if we were to convert this to an enolate form, a base could either go after this blue hydrogen or this red hydrogen. And this is LDA. I've drawn it out again without the lithium. As a base, this is going to attack a hydrogen. And I want you to think for a second which hydrogen this base would be more apt to attack. And the answer would be that it's going to want to pull this blue hydrogen here because of the steric hindrance that those two isopropyl groups provide. So because these are bulky groups, this nitrogen doesn't want to have to get in here, and all of these carbons are going to interfere with the carbons that are here, and it won't be easy for this nitrogen to extract this red proton. However, on this side, it will be much easier because there's just less carbons in the way. And so that's the reason why LDA is going to make the kinetic enolate, or the enolate that is going to be less substituted with its double bond. So the curved arrow here, the mechanism, just for those who are curious, the nitrogen as base pulls this. We've seen this before. These electrons are going to make the double bond over here. But we're going to have this lithium bonded with the oxygen. And the reason is that I think about these kinds of compounds right here as we've trapped it in the enolate form. You could kind of put this in a bottle. You could get a quantitative amount of this enolate. It's not going to interconvert back in between anything as long as you're in a nonpolar solvent. It's going to stay just like this for synthetic purposes. This is the other pathway that I was talking about, and this would make the thermodynamic or more substituted enolate. So again, I'm going to draw on those two hydrogens, and this is what the TMS looks like, TMSCl, and this is pyridine. Now, pyridine is a base. This amine right here is not as basic as LDA, but it still is a base. And the way that this is going to work is that in the first step, oxygen has this really high affinity for silicon. And so we're going to do this SN2 reaction here where chlorine is going to be our leaving group, and this silicon molecule, or silicon atom, sorry, is going to bond with the oxygen. Now, once we get to this point, pyridine is going to be a strong enough base that it will extract that proton, and we will create this silyl enol ether. And so you can see this looks very similar to an enol or enolate, except we still have this silicon atom with the 3 methyl groups attached to the oxygen. Now, we can't alkylate yet, which means we can't have that alkyl halide molecule to add on our carbons. We've got to get rid of the silicon. And to get rid of the silicon, here, that might have been slightly confusing, but I just want to show you that this is the same molecule that we just had before. We can introduce lithium, methyl lithium. And what methyl lithium will do is the silicon will attack the methyl group here, and so you'll get tetramethylsilane. And again, we will have captured our enolate here that has the lithium bound to the oxygen. But notice this time the double bond is on the other side, the thermodynamic enolate. Oh, that's what the arrows would look like. Remember that lithium is a metal, so it doesn't want a lot of the electrons, so you can kind of think about this as this methyl group here has a lot of negative character to it, and so if it attacks the silicon atom, we can make this. Alright, so here's just another side-by-side comparison for making these synthetically useful enolates. That is our starting ketone. With LDA, we'll eventually make the less substituted enolate, but with the TMSCl, pyridine, and methyl lithium, will make this thermodynamic more substituted enolate. Now the next step here would be to alkylate, and when we alkylate, we'd alkylate with a alkyl halide. In this case, we've got these two bromine containing compounds. I guess both of these would be bromoethane. And so if we reacted this molecule with bromoethane, we'd see those two molecules from bromoethane would end up right here. The two carbons would end up right there. And if we reacted this molecule with bromoethane, the two carbons from bromoethane would end up down there. So you can see, depending on which pathway we choose, we are alkylating in different places on our ketone. Now, another really important note is that not any alkyl halide works for these synthetic reactions. It has to be a primary, allylic, or benzylic. So this is primary, so that would work. This is benzylic, and this is allylic, so we could use any of these three, but this secondary bromide and this tertiary bromine compound would not work. And the reason it wouldn't work is because enolates are basic. I'm not sure if I said this before, but an enolate is actually going to be more basic than hydroxide. So between the two of these, this is a stronger base. And as a stronger base, instead of doing a substitution reaction from orgo-1, you should know that secondary and tertiary alkyl halides would prefer to do an elimination. And so if you combined an enolate with this molecule, you'd end up just getting something that looks like this, and over here you would just get something that looks like that. Okay, here is our second to last practice question here. I give you a starting ketone, and I also have listed here 4 different synthetic pathways. And I want you to predict the products from these 4 synthetic pathways. And I've given you a hint here that this third synthetic pathway is actually going to have 2 products, I guess. So watch out for a trick. But this is a very good question. Pause, do it yourself, get the practice in. All right, I am going to go forward here. And here, let me explain all of these one by one. So in this first pathway here, we use LDA. And remember that LDA is going to create the kinetic enolate, or the least substituted enolate, which in our case would look something like, we've got that lithium on there, would look like that, right? The double bond would be on the less substituted side. Then we combine it with this primary alkyl halide. That works, so we should be adding 3 carbons onto this side because, I guess, pretend that lithium isn't here and there's a minus charge. Those electrons would come down, this double bond would go out, and so we're creating a new bond here, and then 1 carbon, 2 carbon, 3 carbons, and that gives us A. Alright, next if we look at B, B is utilizing that the other pathway, the Cl, TMS, pyridine, and then methyl lithium, and so that will create the more substituted enolate, which if this is our starting ketone, would look something more like that with the double bond on the other side. Remember, and this is a common confusion that I think I should address now, sometimes I think a lot of students remember these Grignard compounds, these methyl lithium or alkyl lithium compounds from orgo-1, and that if you had a carbonyl and you had a, let's say just methyl lithium again, because that's usually the confusing one, you could do that Grignard reaction where with acid workup and heat, I guess a little bit of heat, you would create an alcohol. You would alkylate onto here. I just want to make it very clear that this carbon right here isn't the carbon that's getting added in the answer, right? It's this carbon that's getting added on. This carbon is the carbon that ends up attacking the silicon atom. Just something to keep in mind. Sometimes students would add, like in this question it wouldn't matter because both of them are methyl, but in a question down here, they might add just the 1 carbon instead of the carbons attached to the bromine. Anyways, you could see how this enolate would then lead to this compound here, B. 3 is kind of the trick question. LDA would give us that kinetic enolate, the same one that we had in the first synthetic pathway, but if we look at that alkyl halide, that doesn't look primary to me. That looks secondary. And that's the trick here, is that we actually wouldn't do the synthesis the way we thought the synthesis would go. We just have the starting material, and then we would create this alkene here. And so 3 is tricky. Remember, you can't do this with a secondary halide. And then the 4th one is the longest one here, where we start off using the TMSCl pyridine route, and then we also do the LDA route. And so you can imagine in this first step, we would be adding on, here, let me just draw this out really quickly. So we already have the methyl group here. These first 3 steps would add these 4 carbons, and those 4 carbons would specifically get added on this side. And then we would make an enolate again, and this time the enolate would have to be on this side, right? There's 4 carbons here, there's no hydrogen to pull. So then we'd create an enolate on this side, pretend that's not there, and then we'd add this part on the left here. Boop, like that, to get E. Alright, here is the last practice question in this video. Propose a synthesis of this compound here on the right, starting from 2-butanone. And I'm sure you can imagine, but you should be using these enolate synthetic techniques that we were just talking about before. Alright, take your time, pause the video, do this question. I am going to go forward here. And this was my answer. So I start off using TMSCl to specifically create the thermodynamic enolate. Once you use the methyl lithium, that will replace that silicon with the lithium. We can then alkylate. This alkylation is alright because this bromine would be in the benzylic position, and so that alkylation is all good. Next we would use LDA. LDA will specifically create the kinetic enolate on this side, and then we can alkylate again with this allylic bromine to create this final molecule right here. Now I went through that pretty fast. I'm going to take a guess at either a mistake or maybe something that some of you guys started to do and then realized wouldn't work, but probably the most common hang up on this question would be that, and so the correct answer is right here. If you started with LDA, right? So imagine you tried to put on this piece first instead of this piece. You would start with LDA, you would add this on, be going pretty well so far, you'd get to here, but now you have a problem. Both of these alpha carbons are both secondary. And because they're both secondary, you would lose your specificity as far as, LDA creates the kinetic enolate, TMSCl creates thermodynamic enolate. You'd no longer have the choice to use them because neither one would be specific anymore. So you'd get stuck here, and this pathway wouldn't work. So it's very important to realize that sometimes the order does matter here, because you need to have the alpha carbons have different levels of substitution. That's it for the first video on enols and enolates. I hope these practice questions were thought-provoking and helpful.